On mountain tops the world over, astronomers have perched their telescopes. This is the Observatoire du Pic du Midi in the French Pyrenees. And in the hills of New South Wales, a joint Anglo-Australian observatory. In Hawaii, above the clouds, the telescopes of many nations. And in South America, high in the Chilean Andes, astronomers peer into space from the European Southern Observatory. The universe is their field of study. And through the instruments of astronomers, a restless firmament of life, death, and renewal emerges. On Earth, we're bombarded with information from space. Radiation rains down at the speed of light, ranging across the spectrum. In the ultra-short wavelengths, there are gamma rays, conveying powerful images to this orbiting gamma-ray observatory. X-rays from further down the spectrum, gas trapped in a cluster of galaxies, a hint that one day the universe may collapse. From the middle of the spectrum, the telescope gathers visible light, ultraviolet, and near-infrared. The COBE, or Cosmic Microwave Background Explorer, scans across the infrared. This is COBE's remarkable portrait of our galaxy, the Milky Way. At the lower end of the spectrum, radio waves. Gigantic receivers scan the radio heavens for whispers from the beginning of time. And in the wavelengths of visible light, traditional telescopes pursue the wonders of optical astronomy. Optical telescopes come in two forms. One is a refractor. Light is simply collected through a large lens and magnified in an eyepiece. It's the oldest type of telescope. The refractor was first used by the Italian astronomer Galileo. The second, a reflector, was invented by Isaac Newton. Light entering the telescope from the left is reflected back up the tube to a smaller mirror, which in turn bounces the image to an eyepiece. The reflector forms the basic design of most modern telescopes. Its main mirror acts as a huge light bucket. Mirrors can be built much larger than lenses because you can support it from behind as well as by the edges. Here's the view from light rays entering the reflector. First they bounce off the big mirror, then off the small mirror, and finally through a focal point to be recorded and stored electronically. Rather than squinting through telescopes, today's astronomers analyze computer images, or they study pictures photographed through their instruments, or spectrograms showing the composition of stars, and whether galaxies are coming or going. Even the best-placed telescopes have to contend with atmospheric shimmer. Enter the Hubble Space Telescope, designed to observe the cosmos from the crystal clarity of Earth orbit. But Hubble had a problem. It was out of focus. This fuzzy image is a cluster of stars originally recorded by Hubble. But computer correction sharpens the image. Now Hubble is unveiling new vistas. Dust swirling around a black hole. A pair of colliding galaxies. Two more. A catalog of distant galaxies impossible from Earth. a ring of debris before a stellar explosion. Matter jetting from a galactic center. The last gasp of a dying star. The shock waves of a supernova. And finally, in Orion, pictures of young stars with planetary disks. Another Hubble first. The 5-meter American telescope at Mount Palomar was the biggest in the world. Until in 1976, the Soviets built a 6-meter reflector. But it never worked very well. Today, despite fears that a bigger one could never work, the 10-meter Keck telescope is being tested in Hawaii. Deformations in its enormous reflector can be corrected by a series of small mirrors, integrated like a jigsaw. Some of Keck's first images. Here, the Eskimo Nebula. And here, a galaxy. Keck comes online in the late 90s. Meanwhile, at their southern observatory in Chile, the Europeans have developed the New Technology Telescope. Its resolution may rival Hubble's. Compared to Keck, its mirror is small, but cleverly designed to compensate for atmospheric distortion. Radio telescopes work like optical reflectors, collecting information in vast dishes, like this American receiver in Puerto Rico. Radio dishes are large because radio travels in the long waves of the spectrum. Radio observation has a big advantage. Several dishes can be linked to make one powerful receiver. Here, the Very Large Array in New Mexico. And in time-lapse, the Parkes dish in Australia. Radio telescopes around the world sometimes hook up to scan what optical instruments often cannot see, such as ultra-hot gas clouds, radio galaxies, pulsars, quasars. This radio picture from the center of our galaxy may reveal material lighting up around a black hole. Here, a radio telescope shows jets of gas shooting from a distant galaxy, invisible to optical telescopes. And finally, puzzling red clouds flanking a blue galaxy. In one field, radio has been unsuccessful. Dishes continually scan the cosmos for signals from other civilizations. So far, there has been no word.
Amazing Space will return on TLC. Amazing Space now continues on TLC.
A portrait of the Horsehead Nebula in Orion, photographed through one of the most powerful and sophisticated instruments on Earth. It came from down under, the 1.2-meter Schmidt on Siding Spring Mountain in Australia. Operated by the Anglo-Australian Observatory, the Schmidt is the biggest telescopic camera in the Southern Hemisphere. Its cosmic eye requires huge photographic plates, sheets of light-sensitive glass that may be exposed for hours. Schmidt color masterpieces are produced by photographing the sky 3 times, using a different filter for each exposure. But not all Schmidt works of art come from giant telescopes. There's a portable version for amateur observers as well. These photos of Halley's Comet were produced with such equipment: a small telescope and a Schmidt camera with a wide-angle lens. For crisp pictures, the photographer must track the heavens. In this long exposure, the camera locked on to the motion of the stars. This, on the other hand, is time-lapse, where a special static camera takes an exposure once every 30 seconds. Earth's rotation makes the stars appear to turn. Do the same with an ordinary camera, but leave the lens open for a few hours, and the result will be star trails. These star trails are circular because the camera was looking at the southern pole of the sky. The red glow is a rare Australian aurora. This is 2 exposures, a quick one for the star point, a few hours for the trail. And here the camera has been progressively refocused over a long exposure. A pretty effect that highlights the true colors of stars. Mounted between the camera and the tripod is an automatic drive. It compensates for the spin of the Earth and keeps the camera locked in on its moving targets. Using such a drive, a long exposure achieved this picture on low-speed film. With very fast film, a drive is unnecessary. By holding the shutter open for 30 seconds on a cable release, anyone can capture the cosmos. Here's the Andromeda Galaxy, the most distant object visible to the naked eye, and the constellation of Orion from the southern hemisphere, another 30-second exposure. Our satellite galaxies, the 2 Magellanic Clouds, a close-up of one of them, again on high-speed film. An artistic effect. The stars through the glow of a terrestrial volcano. Another in Hawaii, all with a regular 35mm camera. A little house beneath the stars. The trick was to use a flash on the bungalow during a 30-second exposure. The same technique captures people capturing Comet Halley. The lack of a telescope shouldn't keep you from trying astrophotography. This eclipse of the moon was shot on a 35mm camera in central London amid massive light pollution. And here, a partial eclipse of the moon. The moon, with 3 planets, Jupiter, Saturn, and Venus. The heavens are yours for the taking.
Amazing Space will return on TLC. Amazing Space now continues on TLC.
Ideally, we humans would like to see the universe in person. To romp and ride on the surface of other planets as we did on the surface of the moon. But manned missions, however popular, are risky and expensive business. Especially when robots can do the trick. In the late 1990s, this Russian robot may be exploring the new world of Mars, reconnoitering for a manned landing. And this American robot could be gathering Martian samples for dispatch to Earth. But robots are nothing new, certainly not Russian ones. The Soviets built this rover to explore the moon. Under test here, it was to be remotely controlled from Earth, a development spurred by the failure of the Soviets' manned space program. Lunokhod and its successors performed admirably on the moon in the 1970s, returning television pictures and eventually lunar samples to Earth. But by far, the most successful of the robot explorers were the 2 Voyager probes, launched by NASA in 1977. powered by nuclear rather than solar energy. To survey the dark outer reaches, they've unveiled the giant planets, like Saturn. Voyager's successor will return to Saturn early next century, a Euro-American enterprise named Cassini. Cassini will drop a lander on the Saturnian moon, Titan. When Voyager flew by, Titan was shrouded in haze. By soft landing a robot, Cassini should reveal the surface. This planet-sized moon, with its nitrogen-rich atmosphere, is tantalizingly like Earth in a deep freeze. As Cassini departs Titan, it'll move into orbit around Saturn. A robotic eye that will keep this breathtaking planet under permanent surveillance. This robot packs a sting. Another Euro-American venture, as yet unscheduled, to land on a comet. No astronaut would survive this journey. Instead, a hefty reinforced dart, jam-packed with sensors, will probe this dusty snowball. Like a syringe taking a blood sample. It will then beam its data via the mothercraft back to analysts on Earth. This chunky robot Galileo was launched in 1989. The shuttle that launched it didn't have the power for a direct shot. So to gather momentum, Galileo had to swing once around Venus and twice around Earth. The objective was Jupiter, a 6-year journey to the giant of the solar system. Once there in 1995, Galileo goes into permanent orbit and deploys a probe. A kamikaze plunge toward the planet. With only one chance of success, data must be gathered and zipped to Galileo. Within minutes, the probe will be consumed in the crushing Jovian atmosphere. Less dramatic, but equally significant, is the role of robots nearer to home. Earth is girdled by thousands of them in the shape of artificial satellites. Eyes in the sky that keep the planet under constant observation. 3 satellites in geostationary orbit over the equator can cover the entire globe. A 4th is just a bonus. Satellites work in many ways, for telecommunication, navigation, and espionage. They also tell us much about our planet. Here, for instance, is the Earth's topography. Red and black for the highest regions, light green for the lowest. And this is the planet in relief, with shading to emphasize uplands. These are Earth's differing terrains, from composites of satellite data. Soil types. Greenland, covered in ice, appears black. The ecosphere. Ice cover in red, and deserts in dark blue and purple. City lights the world over. In green, the concentrations of life in the oceans. Here, the distribution of plankton, the microorganisms vital to marine ecosystems. And here, an extraordinary satellite image of ocean contours. The surfaces of the seas, far from being flat, mimic the ridges and valleys of the ocean floors below. In the end, it may be these robot explorers, with their eyes fixed on our own tiny patch of the universe, that prove most revealing, monitoring our effects on Earth's oceans, skies, and lands. Their perspective, a constant reminder of the finiteness of our extraordinary blue planet.
Visit the world's great telescopes and find out how to buy one for yourself as the Learning Channel continues to explore the wonders of amazing space. Next.